Okay, I will just have to download it. Okay, so the recording restarted. So what I will do if I were you, maybe you shouldn't rely on the recordings for this week until the issue is solved. What I'm gonna be doing is I'm gonna be uploading some companion videos. So if you go into Canvas, all right, so most of you are in class anyway. So just take it as a normal class on campus, right? Just go to class, you see what I'm doing in class, you take your notes, and then you're gonna go and in announcements, there are gonna be videos of sample problems. So there are 2 already here that I uploaded yesterday, and there are gonna be a few more I'm gonna be uploading on the next few days. With the labs, what you should do probably is, if you can record it yourself, it will be the best. I think for the labs, you should start recording it yourself with your phone, with the computer, right? Until the issue is resolved, right? Because I cannot upload any videos from the lab. And just make sure you are in class, in the lab. With the classes, as I said, I'll be uploading these videos, which are gonna be basically how to solve problems on Coulomb's law, potential, and I'm gonna be uploading on capacitors and circuits as well this week. So that should be okay, plus what we do in class. And for the lab, as I said, if the issue is solved by this week, you should try to record it yourself, right? Because it's gonna take me time to record it and try to upload it. And ask any questions. Plus, I'm gonna be offering office hours. Like today, there's office hours at 11 a.m. So you can log in for half an hour and then we can discuss any questions you may have. All right? So as soon as the meeting is about to expire, I will be sending another invitation and I will wait for everybody to log in to continue with the class. So right now, there is all of you are in class, so that's good. And please, if you have any questions, make sure that you use your microphone or you can just type the question on the chat.
Hello, Professor. I have a question about the quiz that we took last time. I just don't know how can I check. I knew my grades, but I want to know what did I did wrong. So where should I go to see that? Did you do like any comments or anything like that? And like
yeah, I believe I made comments in every quiz. Does anybody else have issues with that? You cannot
where can I find that? Like where should I go to look at my exam?
Did you submit it via Canvas?
Yeah, I did it normally, yes.
What's your name?
Angie Soliman.
Okay. I made a comment in your quiz and I graded. If you access your quiz via Canvas again, you should see the comments.
I am at Canvas. Where should I go? Like announcements, assignments?
No, quiz, where you uploaded your quiz.
Okay, let me see.
If you guys go back to where you uploaded your quiz, you should see the graded, the quiz already graded there.
When I upload it, I did upload it in assignment. So yeah. I see it says quiz test 2, whatever. Final exam. I don't have anything like that. Oh, quiz 1. Close. It says close.
Can you access your file?
Yeah, I see it. Got it. Thank you.
Okay. Yeah, that's how you have to do it. You have to go back where you submitted. All right. Let's see what feedback you had. All right. Let's start with a few concepts before we go into capacitors or more in depth into capacitors. A few things I wanted to comment about capacitors, which is related to the quiz, was the idea behind the energy conservation inside a parallel plate capacitor, right? So if you had this situation, right? Some of you, or actually when I did the solutions, I didn't realize that the electric field was going on this direction, right? That was the direction of the electric field. Now the electron was being shot, so this is the electron, from left to right. So why I didn't notice that is because you will expect the electron to go towards a positive because it's being ejected from the negative plane, right? But the reason why this is happening is because the electron had some kinetic energy. So it had some speed. So you gave some sort of an impulse, all right? So you go like this. And then, even though the electric field is going from left to right, the electric force is going on the electron towards the left. So the electron is losing energy. Why is that? Because when you have a positive charge and you have an electric field going like this, then EQ, which is the force, points on the same direction. This is the force, the electric force. But when you have a negative charge, and that's why I explained also last class, and the electric field is also pointing on this direction, the electric force is actually going on an opposite direction. So the electron was losing energy. That's why the speed was less than the one at the beginning. Okay? In terms of energy, you will say that kinetic energy initial minus kinetic energy final equals to what? To the change on potential electric energy, which is QV or Q delta V. All right? That's what you have to, that's what you can use now in chapter 16 and then 17. All right? So that has to be clear, and that was the tricky part when it was an electron. All right? Okay, so for people who submitted, I think there was only 2 of you who submitted the exam later via email. Your quiz should be uploaded today after class. All right? If you submitted via Canvas, then I can just use the Canvas submission to upload your feedback. But if you did it via email, it does take a bit more of time. That's why you cannot see it yet. But you will see it after class today. All right? Okay, so right now there's still no issues with the time, and it's recording, so that's good. Okay, something I made last class as well, a correction, is about the energy stored in a capacitor. So this is a parallel plate capacitor. All right. You know the electric field goes from left to right. So we have this electric field. The electric potential can be found by knowing the distance between the plates. So the voltage, the electric potential is equal to minus E times the displacement or the distance. So in terms of magnitude, so the magnitude of the, or the absolute value, sorry, of the electric potential will be ED, that. With the energy, however, with the energy, the equations for energy are as follows. So the energy inside the capacitor we know is, we can find it as QV or Q delta V, right? If we use the equation of a capacitor, we get Q squared over 2C or 1/2 CV squared. The square was on the voltage. All right, those were the equation for it, because remember, we defined the capacitance as Q over V. All right, now, there is a relationship because normally these plates are rectangular or square plates, all right? And we know the distance between the plates, and if we were to do an experiment, we will see that the capacitance depends on the area of the plates, how much charge is stored, and the distance between the plates. So what you should know is that the capacitance can be defined as E naught area over the distance between the plates. That's the equation that, or that's the other equation that you should know for the capacitor. Okay, so a parallel plate capacitor, the equation will be the electric permittivity of free space times the area divided by the distance. So the larger the distance, the less the capacitance. The larger the area, the more the capacitance. All right? And then we're going to get an equation of energy using this definition and using this definition and this one here. All right? For now, let's focus on this because this is going to help you for assignment number 3. Assignment number 3 has equations where you have to find capacitance. You just use that equation. Remember here that E naught is a constant equals to 8.85 times 10 to the negative 12 farads per meter. All right, a farad or faradio is a unit of capacitance. Q is in coulombs, V is in volts. Now, very important before we go to the slides. When you used to go to Radio Shack, or even if you want to buy capacitors in Amazon or eBay, right? Normally you find those capacitors in micro, nano, or even in picofarads, right? It's very weird to find them in milli, right? You can find 1,000 microfarads maybe. And the reason you find them like that in those units is because the capacitance of a capacitor is normally very small, right? And if you think about it, it makes sense based on the equation and based on this equation here. A charge is a multiple of the charge of the electron. And normally we discuss charges in nanocoulombs, microcoulombs, or even picocoulombs. And voltages for batteries can be 1.5 volts, 9 volts, 6 volts, 5 volts. So the ratio between Q and V is going to be also in the order of microcoulombs. So that means that your capacitance will be very small. But also if you look at this equation and at a constant, right, it makes sense. You have here 10 to the negative 12, right? Regardless of what area and what distance, your capacitance will also be very small, all right? So it's very important that you realize this, that the capacitance of a capacitor is normally in the units of micro or picofarads or nanofarads, okay? And the same happens with the energy. It's not a lot, all right? But still, it's an electric device that we can use a lot for experimentation, all right? What we have here now, so on the slides, here you have an example of a capacitor, 2 conducting plates separated by a distance d. As I showed you before, the plates can be rectangular or square plates with positive Q, negative Q, positive V, negative V, and the electric field going like this. So basically this is what you had to do in the lab, right? For that last experiment, you had to trace the electric field lines, and the equipotential lines are perpendicular, in this case, horizontal lines, right? This is the equation for the capacitance, all right? The SI units are coulombs per volt or farads. Now, in a vertical type of capacitors, you have the electric field going like this, the distance, and you have the equation for capacitance. All right, this equation actually can be proven, all right, just by using the definition of Q and V, right? For now, let's not worry about that. What I will prove is the equation for energy and energy density that is going to be very important for later in the course. So remember, in terms of general properties, right, the capacitance increases as the plates become larger, and it decreases as the separation becomes larger as well, right? That's common for every type of capacitors, not just for parallel plates, right? We can have spherical capacitors, cylindrical capacitors, it still happens. The equation for capacitance is different, all right, for a spherical capacitor or a cylindrical capacitor or a ceramical capacitor, but the properties of the distance and the area are the same. The larger the area, the more charge that you can collect, the more energy you can store, all right, and the more capacitance you have. And then we have the concept of dielectric, right? When you guys look around yourselves, cables, coaxial cables, conductors, insulators, you will see that copper cables or even internet cables are covered by rubber, by dielectrics, by insulators. We do that in a capacitor to lower the potential and to increment the capacitance. In other words, we can also increment the amount of polarization in the material. All right, so as you can see, we can place this dielectric, and then all the atoms inside the region of the dielectric are polarized, right? So it's very important that you sort of realize that, okay? Now, in terms of the dielectric, we have several types of dielectric that we can find, right? See the list there? We can have water, which is the one that you use in electrochemistry, right? When you do the cells, the galvanic cells. You can also have Pyrex, mica, or even paper, right? So it's very important that you realize that the dielectric is characterized by different constants, right? And the constants are given there. Now, interestingly enough, water has a very high constant, right? But it still is not considered a poor dielectric, right? In fact, in electricity, right, in experiments, we normally do not use water as a common dielectric. What we use the most is mica, rubber, right? Teflon, right? Because of their properties. Oops. Anyway, now that's the equation there for energy, all right? As you can see there, those are the two equations that I already introduced for the energy, all right? Okay, let's prove you now this equation for energy density on the board. Let me just check the time. So I don't want to be surprised when this expires. So we have these equations here, right? Let's use the equation for, and this equation that I'm going to show you right now is a general type of equation, all right? So you can use it for anything, okay? However, I want to take this time to show you the energy density of an electric field, which is very important. All right, so we have the capacitance as E naught area over distance, right? We also have that the capacitance is defined as Q over V in farads, right? And we also have that the energy of a capacitor is 1/2 CV squared. I want to use this equation here. So these equations are very important. You're going to be using them a lot, all right? But now let's combine this equation with these two. So the energy will be 1/2 capacitance is this, right? And voltage, remember here, the absolute value of the voltage is this. So voltage squared is just the electric field squared times the distance. If you have that, right? If you have that, then, so V squared, you will have 1/2 E naught area over distance times E squared D squared. So then the energy will be 1/2 E naught E squared area distance squared over distance and distance. What's area? If you have a parallel plate, the area of the base times the distance is the volume. So we can say that the energy is 1/2 E naught E squared times the volume. Therefore, we can call all this term here the electric energy density of a capacitor, or in term, or in general, the electric energy density mu E. That's what you can define. And we define that very neatly, right? Because we are going to be using that later when we combine this with magnetic fields. So important, right? We can write it here now that the electric energy density mu E is equal to 1/2 E naught E squared. As you expect, it depends solely on the electric field. Okay, so that's basically what you guys have here on the slides. How do I? Oh, sure. So on the slides, you have that there, right? Is the electric energy divided by the volume. And then you have the summary of the chapter. So we finished with chapter 16, right? The only thing left right now is to combine capacitors in a circuit. Well, I want to do that later. What I want to do now is I want to start doing some problems similar to the ones in the web assigned. I have people asking some questions about them. But before we go into problems and examples, I want to know if you have any questions about what we just did here. Any questions? No? It's all being recorded now, so what I want to do while we are doing the office hours today is I'm going to be compiling all these recordings, right? Hopefully the recordings from last week will be recovered. If not, before the midterm. Oh yeah, by the way, this week we have our second quiz on Thursday, chapter 16 and 17, part of 17 at least.
We are having a quiz on Thursday.
Yes, we do, second quiz. And the midterm is gonna be Thursday the 16th. You know why? Because there's not gonna be labs Thursday the 16th. I wanna give you a break. All right, so I want to tell, no labs Thursday the 16th, but that's the day of the midterm. All right, so we're gonna be covering up until what we do on the 14th, because the 15th, I will use it for review. And hopefully we can go over the things that we lost in recordings on the first week. All right, So the 15 we do review, the 16 is not the midterm, sorry, the first test. The first test. So we have lab tomorrow, we have lab on Thursday, we have lab on Tuesday, no lab on Thursday. All right?
So we're having our exam or our quiz on Thursday. Test.
You have a second quiz on Thursday the 9th, and the first test, which is a test of cumulative, chapter 15, 16, 17, on the 16th. All right? Okay, so let's do some problems now. Let's start with conservation of energy. So what is the assignment here? All right, so we have now a proton, so not an electron. It's going to be similar to the question in assignment number 2, the last question. All right. If the meeting is about to expire, please somebody let me know, because I'm going to be mostly looking at the board. All right. So let me know so I can open a new meeting. All right. Anyway, so a constant electric field accelerates a proton from rest through a distance of, let's say, 1.5 meters. Right. Let's make it easier. So we have a proton that starts from rest and there is an electric, no, it just covers a distance of 1.5 meters. So they give you the distance it travels. So delta X, the displacement as well, because it's going straight anyway, 1.5 meters. And then it starts from rest, and then it acquires, it gains a speed of 1.4 times 10 to the 5 meters per second. Not as much as an electron, because it's way more massive than the electron. In fact, the mass of the proton is 1.67 times 10 to the negative 27 kilograms. And the charge of the proton is the same as the charge of the electron. All right? So the first question they ask you is find the change in the proton's kinetic energy. So we're going to find the change on kinetic energy, which is KE final minus KE initial. This one is 0. So the KE final will basically be 1/2 the mass of the proton times the final velocity of the proton squared. Right? Very weak, not much. If we pull the calculator, we have 1.4 times 1.4 times 1.67 divided by 2, 1.64 approximately. So 1.64 times 10 to the negative 17 joules. Right? So that will be the answer there. That will be the answer. All right, for the change of kinetic energy. So because the proton started from rest, that was simple. Find the change in the system's electric potential energy. Is the same. Can somebody argue why is the same? So A and B will have the same answer. The change in the system's electric potential energy is the same as the change in kinetic energy. Right? Is that clear why? It is because of conservation of energy, right? This guy is also Q delta V, right? So technically, I don't need to find the electric potential to do this. However, for part C, you will need it because they ask you for the magnitude of the electric field. So how do you find the electric field in these type of situations where they don't give you time or acceleration? You find the electric potential first, and then you know electric potential divided by the distance will give me the electric field. So let's erase this and let's do part C. Part B is the same answer. So for part C, they want you to find the magnitude of the electric field. We know that the electric potential, the potential difference, is equal to electric field, the magnitude, times the distance, right? Let's put here for now, like that. That's what you also did in the lab. But how do I find this? I have that, how much was it? 1.64 times 10 to the negative 10 was the change of electric potential. So was Q delta V. But I know Q, that's the charge of the proton, which is 1.6 times 10 to the negative 19. So my electric potential will be this divided by that. It's going to be huge. It's going to be 1.02 times 10 to the 9 volts. It's a lot. It needs to be a lot because it's a proton, right? So now that I have the electric potential.
Wait, I'm sorry, Professor.
Yeah.
Q times the change in V is the potential energy?
Yes, this is.
Okay.
Yeah, so this is the potential energy. Right?
Okay, thank you.
Be the change in kinetic energy.
Okay.
All right, by conservation of energy. That's important. Once you have that, you can find electric potential. And using this equation here, the electric field, the magnitude of the electric field is equal to the electric potential divided by the distance, 1.5 meters. Right? And that gives me 6.8 times 10 to the 18 volts per meter. That's how you do the question. Are there any questions about this? It's weird, it's not expiring yet. Are there any questions? That's basically one of the main objectives of chapter 16 is to understand the relationship between electric field, potential, and energy. All right, we've done already problems on how to calculate potential. We're gonna do one more later, but for now, I wanna make sure that this is clear. All right, let's go into capacitors. All right, so now I will do a few examples like in the assignment 2 still, because there's a question here with capacitors. So let's do that, all right? And then let's do a few like assignment number 3. So far, there is no problems. Hopefully, they already fixed the issue. And we can also recover those recordings. All right. Anyway, so a typical problem with capacitors, I tell you, is you have a 9-volt battery. So you have a capacitor here connected to a 9-volt battery, which we label it like this, by the way. The large is the positive terminal. The small is the negative terminal. And then current goes, well, we're gonna talk about current later. So this one is a battery like the one you can find on the store, 9.0 volts. And they tell you that there is a charge stored. So positive Q, negative Q. The charge stored in total here, right? That charge is of 30 30.0 microcoulombs. Find the capacitance and find the energy stored. Easy. The capacitance is Q over V. So Q is there, but we use 30 times 10 to the negative 6 divided by 9. That will give you 3.3 with a period times 10 to the negative 6, or 3.3 with a period microfarad. See what I did there? Right? I changed the units to microfarads. Right? So that's easy. Application of formula. And then to find the energy, I erase this, fine. Always with small. Right? There. Yeah. So the energy stored 1/2 CV squared. Let's use that because I don't have to divide here. So 1/2, the capacitance is 3.3 with a period times 10 to the negative 6 times the voltage squared. This was 9 squared, 81. So if I'm to multiply that, I get exactly 270 divided by 2, 135 times 10 to the negative 6 joules. Or actually, let's use the units, 135 microjoules. Right? So that's basically how you do a question with capacitors. All right, a parallel plate capacitor. Let's now re-review and let's find now an electric potential taking the 0 at infinity on an arrangement of charges as the one I'm going to show you now. So let's review that now. Remember that the electric potential is a scalar, so we can use that in our advantage to find the electric potential and also the electric energy. This should help you also for the assignment. Okay. What they give you is free charges on a rectangular chain, like this. Let's use those values 8, 2, and 4 microcoulombs, all positive. So 8 microcoulombs, 2 microcoulombs, 4 microcoulombs. This will be just whatever distance is fine. Let's make this 6 centimeters, and let's make this 8 centimeters, right? We want to find the electric potential taking 0 and infinity at this point P. So we want to find the electric potential at P. And then we can find the energy of the system. So to find the electric potential, we can take we can use this. The potential at P is equal to the potential due to 8 plus the potential due to 4 plus the potential due to 2 microcoulombs. The only thing I have to remember is that I need this distance, and also this distance here, right? If this is 6, 8, and this is 19, so this is also 6, this is also 8, and all this is 10 centimeters, right? By doing Pythagoras. But these are centimeters, so we have to be careful. Here, the potential on 8 will be K Q over the distance squared, but that's 8 centimeters. 8 centimeters is 0.08. Remember, right? 0.08, you divide by 100, and it's just a distance, not distance squared. That's the equation for electric. KQ over the distance. That's the equation for electric potential. And we do the same for these two. K 4, and for 4 the distance is 6, right? And then for 2, divided by 10 centimeters, that's actually 0.1. 10 divided by 100. I can't do this in this case because it's a scalar and all of them are positive, so all of them are positive. What I will do now is I will factor out K, so K is the same, but also 10 to the negative 6. So K, actually, what's the value of K? 9 times 10 to the 9 times 10 to the negative 6. I factor that out, I open parentheses, and then I do 8 over 0.08. 4 over 0.06, 2 over 0.1. This will be 9 times 10 to the 9, 10 to the negative 6, 1,000, so 9,000. And here I have 100 plus 20. This one is, so I need a calculator for that to give that value. 6.7. Any questions? What I'm doing right now? I mean, it's application of formula, but still. Because the equation for potential is KQ over R. KQ over R. Don't forget. All right, it's not electric field we're finding. We're finding the electric potential. All right, so the equation for electric potential is KQ over R. And the equation for electric field is KQ over R squared. All right, so be careful. All right, and it's a sky. So if I do my math there, divided. Oh, okay. Oh, yeah. 20 plus 66.7 times 9,000 divided by 1 million. 1.68 times 10 to the 6 or megajoules, 1.68 megajoules. Is that clear? That's very identical to a question you also have in the assignment. Question number 4. They don't ask you for the energy. What they ask you is do the same if now this charge is negative. So if the 2 microcoulombs, you may have different values, of course, is negative. So what happens with the calculations if 2 is now negative? The only thing that you have to do is here, this will be negative. So this is part A. Part B will be when that is negative 2. So negative, 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 right? And then all this becomes 166.7 minus 20, right? So my energy will be less.
Professor, why are the units joules? I thought they were volts.
That's for voltage. Oh, sorry, yeah. That's right. It's volts. Yeah, sorry, the units are volts.
Okay,
The units are volts, sorry, that's my bad.
thank you.
So 100 plus 66.7. 100 plus 66.7 minus 20 times 9,000. 1.32 megavolts, right? The units are volts, that's right. Mega is a million, all right, 10 to the 6. So that's what you have to do for that question, all right? It's just, we're just finding the electric potential, all right, just using that equation. We did not find energy on this question, all right? And that should cover all the details for assignment number 2, and questions like this will be on the test next week, and on the quiz this week will be similar, 3 to 4 questions, all about electric potential and maybe 1 about capacitors, all right? In fact, let's do that now. Let's go into sort of capacitors. That's assignment number 3. Let's see. Is this one question? Yeah. So capacitors is easy in terms of the concept, but what you need to be careful is with the units. So let's do a problem where I'll do a few combination of units so you know how to work them out. All right? You don't have to draw them. I just want to draw them so you can see the interpretation of the problem. But in many of the problems, they describe you and they give you all the information that you need. So let's start with that now. And remember again, capacitors is a direct application of electric potential and electric potential energy. So the problem reads like this. An air field, okay, first of all, they tell you that it's a air field capacitor. Why do they tell you this? Because you are gonna see later on as well that the properties of air and that of vacuum are very similar. For example, in terms of refraction of light. When we start doing refraction of light, you will see that we define refraction on vacuum through another medium. And then later we will take the properties of vacuum as the ones on air, the properties of air as the ones of vacuum. So when I said, for example, that E naught is the permittivity of free space, I can say that this E naught can also be applied to air, right? Because the electric capacitance for air is very tiny. It's 1.00008 something, right? So you can approximate it to be 1, right? So that's important. So when they tell you it's an air field capacitor, that means no dielectric. And then they tell you that the area of the plates, so they give you this, they tell you that the area of the plates is 7.5 centimeters squared. And the distance between the plates is 2 millimeters. So distance 2 millimeters. The electric potential that you're applying, so this is at 24 volts. So it's connected to a battery that is providing 24 volts. The first question, find the, let me see something here. Okay, find the magnitude of the electric field. All right, so we're gonna find, that's the first thing they ask you. How will you do that? It's very easy. How will you find the magnitude of the electric field? Given that
Did you do the distance times the voltage?
the voltage divided by the distance. So
I'm sorry, yeah, sorry.
Divided by the distance. The only thing you have to be careful is with the units. So 24 divided by the distance in millimeters, 2 times 10 to the negative 3 milli. That will give me 12,000, exactly the same as what you had in the, right? There you are. 12,000 volts per meter. Find the capacitance. So it's a parallel plate capacitor. I have the area and I have the distance. To find the capacitance, what do you use? E naught area over distance. That's what you use. E naught is not given on the problem, so you need to have that with your notes. Where do I have a space for that? Let's do it here. So E naught is 8.85 times 10 to the negative 12 Faraday per meter. So I'm gonna do it here, right? 8.85 negative 12. All right. The area is 7.5 centimeters square. The area cannot stay with those units. You have to change it to meters square. How do you change this to meters square? 7.5 divided by 100 twice because of the square. So basically times 10 to the negative 4 meters square. Does everybody understand this conversion? Does everybody understand? Because at some point you may have to change millimeters square to meters square. So you need to be comfortable. Do you understand what I did there? Right? I divided by 100 twice because it's centimeters square. So that's good. Now I want to compute the capacitance by multiplying by the area and dividing by the distance. And now I use a calculator, right? Now, they want you to write in a given type of unit here that I want to show you now, because it's going to be very small. 8.85 times 7.5 divided by 2, that's 33.20. Right? So just the numbers. So let's put that in here. The capacitance, I get, yeah, 33.20 times 10 to the negative 13 farads. All right. You are not supposed to write it like that. The problem is asking you to write it in pico farads. 1 picofarad is equal to 10 to the negative 12. So that will be 3.32 pico. Does everybody understand this? Yes. The physics is easy. What I want to make sure is that you understand the mathematics. Is that clear? Right? I found the electric field there, and then I found the capacitance here. And that's the only thing they ask you. They don't ask you for the charge or anything else. All right. Any questions about this so far? You're good? Assignment number 3, you guys should start it today. All right. The office hours, I'm going to be answering questions about that. And also about the lab, if you have any. All right. What I want to do now is, before we do more problems, we need to introduce the idea of arrangement of capacitors. So I want to use a whiteboard because I feel more comfortable using that, but that's also in the slides on chapter 17. All right, chapter 17, let me see, that is here, which is in modules. You guys will have access to capacitors in series. Should I be here? Storage. Oh, I see. Yeah, that's because it's in circuits. That's fine. So you're gonna need to copy this down then. Or I will also send you a few examples, but make sure you're writing this down. It's not a lot, but since now we're gonna talk about circuits, it's at the end of the next chapter. So it's at the next chapter, but it's at the end. So let's introduce capacitors in series, capacitors in parallel. First of all, let's talk about the idea of a circuit. So far we have introduced concepts of electric field, electric potential, electric forces before that. So now you know that a charge can move due to an electric field, that there can be energy change. There can be a potential difference because it goes from higher to lower potential. So as the charge moves, right, there is a transfer of charge. And when you divide that by time, the rate of change of charge per time, per unit time, you will get a concept of current. That is the idea of chapter 17. But before we start discussing that, we need to discuss how charge is distributed on a circuit. So a circuit is a closed environment. It's a closed loop where you can have devices, switches, batteries, capacitors, and later on resistors, and later on inductors, right? So the idea with the first type of circuits is to have capacitors in series. So let's draw them out here, all right? A group of capacitors in series will normally look like this. C1, C2, C3, and then there is a potential A here and B. So there is a potential difference in between. We call that V now. And remember, this was C1, C2, C3. What do we know about, what's the first thing we know? Q over C is equal to V. That's the first equation that we know. What you should know is that the conservation of energy and the conservation of charge is always true. So we have here V1, V2, V3. And by conservation of charge, we have Q, 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 the same charge, because it's in series and it's connected to this potential. The three of them are connected to this potential. So Q has to be the same. So what we know is that V is equal to V1 plus V2 plus V3. Perfect. But what is V? V is Q over, I'm gonna call this C equivalent. And what is V1? Q over C1, Q over C2, Q over C3. Perfect. What happens? All these Q's cancel, and I have the equation for capacitors. Capacitors in series, guys. 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. This is a very important equation for capacitors in series. So this is for series. All right, nice. So we have that, right? Now let's do capacitors in parallel. All right, so we're going to be using those equations now as well. So this is in series. the equation right there for now. And let's look here. Capacitors in parallel. And as you're probably guessing, a parallel set is like this, like parallel lines. C1, C2, C3, and they are all connected to a power supply or a battery. Again, V, let's call this C1, C2, C3. Now, when you start working with circuits, which is gonna be this week actually, yeah. This week you're gonna start doing arrangement of circuits in the second lab this week, right? You have to understand that in parallel, or when you do connections in parallel at home, right? One advantage is that one of these, it can be resistors or light bulbs, can die. But the other two are still non-change. If that happens in series, then the whole circuit is messed up. So that's why we use parallel arrangements a lot in electricity. Anyway, so this one, because this point and this point are at potential A and B, and the difference is this, then this is also A, this is also B, B, B. So what does that tell you? That V1 or V is equal to V1 equals to V2 equals to V3. The potential is the same. So how do we use the conservation of charge? Q of the circuit is equal to Q1 plus Q2 plus Q3. But remember, Q equals to CV, or Q over C is equal to V. That equation is the same. So what I want to do here is, what's Q? C equivalent times V. But all the V's are the same. It's fine. So C1 V1, C2 V2, C3 V3. But all the V's are the same. V, V1, V2, V3. So C equivalent C1, C2 plus C3. This is in parallel, that one is in series. So we just proved the equations for capacitors in parallel and capacitors in series. Very neat, right? Very nice, and very nice that we didn't have any issues with the recording. So that means that they probably already fixed it. So regardless, from now on, guys, because we might have those issues again, what I'm gonna do is, as soon as the recording is available, I will download it. So from now on, it will be a file, all right? And if you saw my announcement yesterday, I might use external websites. I used to have a Mega Upload account, so hopefully it's still activated. Or if not, we'll use Dropbox. And I might have like a backup in there, all right? So they will be on Canvas, but we'll start creating backups, all right? In any case, let's solve problems using this, all right? And that's good because that was the objective of today. Do this, because tomorrow we're gonna start with circuits and with current, Ohm's law, all right? Which you already have discussed in the lab anyway. So let's do problems. The best way to understand this, trust me, is with problems. And let me see if I can find, yeah, there is one here. Your typical problems with capacitors like this will be circuits where they ask you a few things. All right. So let's do an example here now. So example. They can give you the following, and the circuits can be sometimes more complicated, sometimes not that difficult to grasp. So we have 2 microfarads, 4 microfarad, like that. And then we have outside of it, and then here the battery, and then here another one, and then here 3 microfarads, 12 microfarads, and the battery is 9 volts, 9.0 volts. The first question is, find the equivalent capacitance in that figure. And then you're going to find the charge on each one of these. And then the potential. So a question like this can have 3 to 4 sections. And there is always a question like this on the test. So let's see how you do it. The first thing you need to understand is that charge is proportional to current. So you can always say that charge is leaving the potential, right? It's going like this. And here, in these 2 points, you have what you know as nodes or junctions. Think like water pipes or like traffic on the highway when you have a fork. Traffic can go on this direction or on this direction. By conservation of charge, we know that this one has to be equal to this one here, that is arriving. And then when they join together again here, they will go all the way back to that point. You don't have to do that in the problems, but this will help you to understand what's going on, right? Charge is being divided in that loop. So these loops, right, you have division of charge. What you should know is that the charge here and the charge here are the same because they are outside of the loop, right? And there is no junction. They are not in parallel in any other capacitor. So let's start with part A. Let's find the equivalent capacitance. The first step will be to get rid of the loop. We have a loop there. They are in parallel. So when they are in parallel, what do you do with the capacitors? You add them together. So 2 and 4, they can be combined into one capacitor of capacitance 6 microfarads. And then 12, 6, and 3, they are all in series. So how do you do the series one? The series, you will do 1 over C equivalent is equal to 1 over 12 plus 1 over 6 plus 1 over 3. Bear in mind that I don't write the units there, I will write them at the end. Now, fractions. Common denominator, 12. So 1 over 12, 2 over 12, 4 over 12, okay. So I will get 7 over 12, but that's 1 over C. So C equivalent will be 12 over 7 microfarads. In decimals, that will be around 1.71 microfarads. Any questions about this? So first you do the loop, and then you do all the ones that are in series, and that's your first part. So that's
Sir,
yes,
why is 12 over 7 again?
because 1 over C was 7 over 12, so you switch it to get C.
Oh, okay.
All right, don't forget to do that. I know it can be because of the rush, you can forget to do that and you get the wrong answer, right? And the thing is that you get this wrong, everything else will be wrong, because we need to use that to answer the other questions. Okay, so please always check your answers. All right, so you have to switch it here. Anyway, so part A, I found the capacitance, right? So now I have to find the charge on each capacitor. This is the first step to do that. You're gonna find the charge on the circuit. What's the total charge? So I'm gonna write it here. Q of the circuit is equal to the capacitance equivalent, the equivalent times the voltage, which is 9. Right? So that will be 1.7, or in fractions, 9 times 12 over 7. So let's see what I get. 12 over 7 times 9. So let's round that to 15.43 microfarad times volts, microcoulombs. That's all the charge that is flowing through here. Automatically, you know that that's a charge here and a charge here. Because as I explained before, they are in series and the charge is the same. However, for 4 and 2, that's not a charge, it got divided. Right? So what you have to do, what I'm gonna do now is I'm gonna move the camera over there so I can finish the problem there. And then I will point it again, but I'm sure you already wrote this down, right? So this was the equivalent capacitance, and here I found the charge on the circuit. Now I know that that's a charge here and here. In fact, you can say here Q equals to 15.43 microcoulombs, and here you can say Q equals also 15.43 microcoulombs. So that's here and here. So now let's go to that side and let's finish it here. What we're gonna do now is to find what's the charge on 4 microfarads, right? To find the charge here, we need to use the combination of these two, which is 6. The charge on this 6 is 15.43. What do they share in common? The voltage. The voltage on 4 microfarads is the same as the voltage in 2 microfarads, which is what? Which is 15.43 divided by 6. That will give me around, should be like 2 point something. 2.57 volts. Let me explain that. The voltage on the circuit was 9, but it gets divided here, here, and there. So the voltage only on the loop is 2.57. So 2.57 volts. So the charge on 4 will be 4 microfarads times 2.57 volts. So then the charge on the 4 microfarads will be approximately 10.28 microcoulombs. Do I need to do all that for 2? No, because the charge here, here, and also here is 15.43. So the charge on 2 microfarads is 15.43 minus 10.28. That's 5.15. So 5.15 microcoulombs. Basically that one, right? As you expect. So I found a charge on each one of these. Any questions about that? On how I found the charge on those two there?
Could you just say that you're just splitting the voltage, the
Splitting the charge.
Splitting,
Splitting the charge.
splitting the electric potential, the V?
Yes, yeah, the electric potential is split among 12, 3, and 6. Yeah, the electric potential is split. But also, when the charge gets to that point, to the loop, there, when the charge gets there, it gets split towards there and towards here.
So could you just do simple,
The
could
charge,
you just say that when you get to the parallel series, that the 2 gets 1/3 of the charge and the 4 gets 2/3, because the relationship between 2 and 4 is
2 to 1.
1 to 2.
Yeah, you can do it like that as well. Yes.
Okay.
You can do it like that as well. So as you saw there, the charge on 4 is twice the charge on 2. Right? How would you find the voltage on each capacitor now? I already found the voltage on 4 and 2, right? It was 2.57 volts, right? How will I find the voltage on 3 microfarads and 12 microfarads? Anybody? Why do you think I wrote Q here and Q here? Because I can now directly find the voltage here and the voltage there. The voltage on this capacitor, let's put here V, will be 15.43, the charge divided by 3. That should be around 5.2 approximately volts. And that one there, 15.43 divided by 12 should be approximately 2 volts or 1.8 volts. Sorry. So the voltage here will be 15.43 divided by 12, around 1.6 volts. That plus that plus that should give you 9 volts. Everything is concerned. Any questions about this? We're gonna do more problems, don't worry. We have time for one more at least. All right, that's basically assignment number 3. Right, to do arrangement of capacitors. Let's do another one that I always find students getting confused. All right, and then with that, we can finish the class. And then after 10 minutes, I will open another room for office hours. All right, that is only if you have questions. If you feel comfortable with the material, try and do the problems yourself. If you have a question about the lab, you are also welcome to come and ask questions as needed. All right. All right. So let's do another problem now with a different setup. And this setup, please pay attention to it, because every semester I see students making a common mistake on that. All right. So I want to erase the board now, and then we can do the last problem of the day. Okay. So the setup now is just one loop, basically. So you have let me figure out the values so we get nice values in this problem. All right. So let's do it like this. You have one there, one here, and then one here, one here. And then you have like that. So let's see. 12 microfarads here. And 4 here. And then you have let's put here 100 volts. Actually, that's too much. 10 volts here. So that's one. And then 2 microfarads here, 2 microfarads here. There you are. So again, find the equivalent capacitance, find the charge, and then find the charge on each capacitor. All right. Part A is the easy part. We're going to find the equivalent capacitance. It's the easy, but it's the one where you can make a mistake. Why? Because I said, right, parallel are where they are like this, and series is when they are like this. Many or some students, what they say is, okay, parallel, and then series. That's wrong. If you do it like that, you're gonna get the wrong answer. And then everything else will be wrong. So how do you look at this problem? You have this loop. These 2 capacitors are in series. And these 2 are in series. So what you should do first is join in series these 2, join in series these 2, and then you will have this. One here in parallel. And these two are connected to the battery. In series here, right? So in series, what you have there is 1 over C equals to 1 over 12 plus 1 over 4. Common denominator is 12. Four over 12. The capacitance is switch 3 microfarads. That's for this guy here. For this one here, let's do it here. 1 over C equals to 1 over 2 plus 1 over 2. That's 1. The inverse of 1 is 1. So C, let's call this C2, let's call this C1. 1 microfarad. So in this picture here, you have 3, 1, and 10 volts. Now, these are in parallel. Now they're in parallel. So the C equivalent, 3 plus 1, 4 microfarads. Part A. Part B, let's do it here. Find the charge of the circuit. Q equals to C equivalent times V, 40 microcoulombs. Any questions about that? So I found first there, and I found the charge. So I have A and B, pretty simple. Part C and then part D will be find the charge on each capacitor, find the voltage on each capacitor. Let's do the charge first, because that's an easy one. As you know, and as I explained, charge goes like this, and it gets divided. But what's the advantage of this setup? As you can see here, what do they share in common?
Professor, can I stop you 1 second? What were we finding in B again?
The charge of the circuit, Q.
Thank you. Thank you.
Find that. So when they are in parallel, this 10 volts is the voltage here and the voltage here. Is that clear? It's not a voltage on there, and there. It's basically the voltage on 3 and the voltage on 1. So you probably already are guessing the answer. The charge here has to be 3 times the charge here. So you have more capacitance there. And the equation is Q equals to CV. But there is also something else that you need to realize. That this 3 is these 2 in series. And 1 is these 2 in series. So whatever charge is here is the charge on 12 and the charge on 4, because they're in series. And whatever the charge is on 1 is the charge on 2 and the charge on 2. Again, because they're in series. So perfect. I can just do the problem and finish it. Let's put it like this. Here. The charge on 3 microfarads is equal to C equivalent, is equal to C, the capacitance, times the voltage, 30 microcoulombs. And the charge on 1 microfarad, without doing the math, 10 microcoulombs, because it's 3 times less. And therefore, Q on 12 is equal to Q on 4 microcoulombs equals to 30 microcoulombs. And Q on 2 microcoulombs is 10 on microfarad, right? 12 microfarads, 4 microfarads, 30 microcoulombs. The charge on 2 microfarads are the same, 10 microcoulombs. And then the voltage, I want to find the voltage on these 4, right? If I have the charge on each one, I do Q over C. So let's do that on this part here, right? So let's write in here, the voltage on 12 microfarads is the charge, 30 microcoulombs over the capacitance, 12 microfarads. This will be 2.5, right? Yeah, 2.5 volts. And the voltage on 4 microfarads 7.5 volts. How do I know if it's correct? 7.5 plus 12 plus 2.5, 10 volts.
Can you turn the camera just for a second? A little over to the left. Thank you.
All right, guys, that's basically what I wanted to do today. We have some time left, so I want to show you the slides for the next chapter where you can find this. I will be uploading some videos as well. All right. That professor that I'm uploading is very well explained. He does problems just like I do on the board, right? And his camera is such a way that you can see the whole thing actually, right? But it will help you a lot to, I think it's better than Khan Academy. You can use Khan Academy as well, but I think it goes more to the point. And the problems are similar to the ones I'm doing here, right? Now, the topics for the second quiz are gonna be more than the first quiz. So there might not be a bonus question, but there will be 4 questions. So at least we'll have more chance. And again, there will be 2 bonus questions, 2 short-ended questions, 2 multiple choice questions, all right? But as you notice from the first quiz, I am giving points for your work, all right? And a couple of the questions may be longer, right? There, for sure, there will be a question. Yeah, there should be a question like this. There will be a question about finding electric potential, and there for sure be a question about conservation of energy. So,
Professor, are we gonna have a bonus question?
no, not for this one, because the grades were actually really high on the first one. So I think you guys are fine. All right. There will be a bonus question on the test. But I think the second quiz, the first quiz, normally I use it like that. Is to measure the class. And I think the class is doing really good. The assignments are also good. So your grades are very high. So for the second quiz, we will leave the bonus question aside, but we will have extra points on the test. All right. Because the tests are harder. That's why you're gonna need more time. That's why you're gonna have the entirety of the class plus more time, most likely, for the test.
How many questions will be on the test?
The test, you might have 7 to 8 questions.
And how many bonus questions?
I don't know yet. I don't know yet.
At least what 4? Please.
The test is designed so you have at least 2 hours and a half to do it. All right? So we start at 9, it will be close at 11. Maybe more because you might need to upload, and it's all short-ended. So there's no multiple choice for the test. All right?
So the test is all open-ended, no multiple choice at all?
Yeah, no multiple choice. Because I think it's the best way so I can see what you guys do. All right? Plus, we've been discussing, because we have meetings every week, about the online, you know, this is the second time we're doing this, the second semester, yeah. And even for the semester, I don't know if you guys know, but the 4th semester is also gonna be online. And it's gonna be synchronous, and expect teachers to not give you many multiple choice. right? Especially for math and science, and the reasons are very obvious. It's the only way we can see if you guys are learning, right? Many of
Professor, is that the
yes,
final decision that they took for the fall? Is it gonna be
yeah,
online?
yeah, yeah.
Okay.
I will do my classes like this. So I hope that at least this is like 70% of what a normal class will be, right? In fact, you have recordings at least for this. So I will do my classes like this, right? With a whiteboard, with questions, and there will be recordings available on that. Unfortunately, that's what they decided, all right? There was the idea of going hybrid, but they are not doing that. So yeah, it should be fine. It should be fine. Like right now, I have double the amount of students I normally have on a semester. And the grades are actually higher. And the questions are basically the same I give in a normal semester. Right? I'm covering the same material. So
Are you saying for all the disciplines at the college, they're going to 100% online? Or
some
just
labs
for,
are going to be in person. I know some
okay.
labs in pharmacy and I don't know in other degrees are going to be in person, but with limited capacity. All right? But first year physics, second year physics, first year chem, second year chem, I know it's going to be, and math is going to be online. But at least you guys have synchronous, right? I teach at Union and it's asynchronous. So it's all based on recordings. They might change that for the fall, but we don't know yet. All right. Now there is a discussion on Canvas where I'm asking you guys to give feedback about the class. All right. So far, the only issue right now are the recordings. So let's hope we can fix that today. All right. But I feel like I'm giving enough time for you guys to write things down and to ask questions. All right. So are there any questions about this problem, by the way?
So you didn't do the potential, the electric potential at 2 microfarads? Because
Well,
it's
at 2 will
basically
be
5 and
will
5.
be 5 and 5, right?
Yeah, okay.
It's the same. 5 volts for each of the 2 microfarads. So if you master this type of questions, it will be very easy once we start doing circuits with resistors. So that's good. And there are also 7 questions on assignment 3. All right. If you feel like you want more questions, guys, because I did reduce the amount of questions this semester. So the only difference between the normal semester is the amount of questions per assignment. So if you want more questions, you know you can go to modules. What's this here first? Oh. Here. You can look at sample problems. Oh, by the way, there's this study guide here. I believe this one has problems on potential. There, right?
Would you mind giving us the answers to those extra problems just so we can see how we're doing?
Yeah, we'll try to look for them.
Okay, great.
Was looking for them during the weekend, and I don't know why I don't find. I don't know. It's because I made them like 2 years ago, but I will look for them. All right. And then for capacitors and current, you have a whole bunch here. You have resistors here. Oh, here I have the answers. So this one has the answers. All right.
That's good. Thank you.
Are there more capacitors here? Sample problems, electric fields. Oh, this current. So there's not many about circuits of capacitors. Well, you have current in there. All right. But then the assignments are already open, so you make sure you finish that first. Okay. All right, guys. It's more than 10:45. I'm gonna stop the recording now. I will start a new office hours in 10 minutes. All right.